In this video, I will show you how to use Newton's second law when you have an accelerating but not rotating frame of reference. So in this case, what I've drawn here is my S sub 0 inertial frame of reference. This is the origin. This is x naught, the x-axis of my inertial frame of reference. This is y naught, the y-axis of the inertial frame of reference. Now, I also have here my S frame of reference, and this one is accelerating, but it is not rotating frame of reference. And I have the origin, the x-axis, the y-axis. Now here is my object, whatever that may be. I don't really care at this point. I'm just going to show you how you can use Newton's second law in an accelerating but not rotating frame of reference. So here is my object, and I am showing some position vectors in this picture. With r sub 0, with r naught, I'm showing the position vector of my object with respect to the inertial frame of reference. With the vector r, I'm showing the position vector of this object with respect to my accelerating frame of reference. And then with the capital R, I'm showing the position vector of the origin of the accelerating frame of reference. Now, let's see, what's the relation between those three vectors? If you look at the picture, if I start from here and I follow the big R vector, and then I follow the small r vector, I arrive at the same point compared to if I just follow the r naught. So this is telling me that r naught is equal to the big R plus the little r. Now, of course, I can take the time derivatives of these. And those will represent velocities, but they are different kinds of velocities. So the first one is the velocity of the object with respect to the inertial frame of reference. This one is the velocity of my accelerating frame of reference with respect to the inertial frame of reference. And the dr over dt, it's the velocity of the object with respect to the accelerating frame of reference. Now, one thing I can do, I can denote, I can say that the dr capital R over dt is just v, uppercase V. So this will be the uppercase V plus this. Okay. Now, of course, I can take one more time derivative. Why not? So what I'm gonna get is the second time derivative of r naught and dv over dt. And of course, all of these are going to be accelerations, but there are different kinds of accelerations. So the first term here on the left is the acceleration of the object with respect to the initial frame of reference. dv over dt is the acceleration of the accelerating frame of reference with respect to the inertial frame of reference, and the r double dot is the acceleration of the object with respect to the accelerating frame of reference. I can use also uppercase A for the acceleration of the accelerating frame of reference. Now, here's the thing. I know that Newton's second law is valid for inertial frames of reference. So if I assume that I am in the classical physics domain, meaning my object is not moving with a speed close to the speed of light, I know that the net force acting on it is approximately equal to the mass times its acceleration. But this needs to be the acceleration in the inertial frame of reference. Okay. Now I can use, let's call this equation 1. Let's call this equation 2. I can start from equation 2 and use equation 1, and this will give me the mass of the object times the acceleration of the accelerating frame of reference plus the mass of the object times the acceleration of the object with respect to the accelerating frame of reference. And I'm going to rearrange these terms. I'll say F net minus the mass times the acceleration of the accelerating frame of reference equals to m r double dot the mass times the acceleration of the object with respect to the accelerating frame of. And here we arrive at this very important result. What we have here is the net force acting on the object, which has, let's talk about units. This one has the units, of course, so newtons. This is a mass times an acceleration, so we have kilograms meters per second squared, which is equivalent to saying newtons, and then we have again kilograms meters over second squared. Okay, we do have consistency. The important part is that this expression does look like a Newton's second law. We have a mass and an acceleration on the right side, and we have quantities that have either the units of newtons or something equivalent to a newton. So this is the application of Newton's second law for the accelerating but not rotating frame of reference. You do need to find all the interactions your system has with the surroundings, so you do have to find all the forces acting on it. But then in addition to the net force, you have to take into account, using minus the mass times the acceleration, you have to take into account the acceleration of the accelerating frame of reference. Okay, this is the acceleration of your non-inertial, okay, it's not an inertial frame of reference. Accelerating frame of reference. So you need to know the acceleration of your non-inertial frame of reference, and you take it into account by including it in on the side of Newton's second law with the net force, and this will allow you to predict the motion with respect to your non-inertial frame of reference. So it is important to understand at the end of the day that all of the interactions that your system has with the surroundings, the actual interactions, they will be included in Newton's second law for this non-inertial frame of reference here. You include the fact that you have a non-inertial frame of reference by including this term. Now, is this term really due to a force? No, it is not. There is no force, there is no interaction that gives you this. So this quantity is not due to any interaction. There is no interaction between the system and the surroundings that will give you this. This is purely due to the fact that your frame of reference is accelerating with respect to the non-inertial frame of reference. Now, does this term, another question more important is, does this term matter for the motion of your system, of your object, with respect to the non-inertial frame of reference? Yes, it does. the acceleration, the r double dot here on the right side, the acceleration of the system with respect to the non-inertial frame of reference does depend on the mass times the acceleration term that I have on the left side. So does this term affect the motion with respect to the non-inertial frame of reference? Yes, it does. If you're using a non-inertial frame of reference, you have to use it. Is this term due to an interaction? No, it is not. This arises, it's purely due to math. It arises because you are using a non-inertial frame of reference. There is no interaction here that gives rise to this. So how do you deal with problems? Okay, you are used to using Newton's second law. In inertial frames of reference, you have F net equals the mr double dot. Okay, the net force equals the mass times the acceleration. What you do if you're studying the motion of an object, of a system with a non-inertial frame of reference, you do the net force as you would do otherwise. You have mr double dot, where r double dot is the acceleration with respect to the non-inertial frame of reference, but then you also include on the left side the minus mass times the acceleration of your non-inertial frame of reference. And then you proceed as usual. Once you have the acceleration, you find the velocity, you find the position of your system, and you have your equations of motion. So once you set up Newton's second law for your non-inertial frame of reference, you proceed in the same way that you would proceed otherwise.